All right, this is for dynamics, the steps 5 and 7. Um, so these are all the calculations I did for calculating the force on the object. So in the videos, it just went over how he went about getting all of the measurements. I know we were supposed to just calculate them ourselves, compare them to the measurements calculated from the force meter in the actual wind tunnel from the videos. So he just went over, the air force basically pushes the object hanging down, which pushes on the force sensor, which measures in newtons. So basically, the force from the air has to do with the velocity of the air squared. So it's going to increase more and more as the force or the velocity of the air increases. It also has to do with the area that the air is coming in contact with, and the drag coefficient of the object itself. So basically, the air will, where it's hitting the object, it will create drag based on the shape. Like a flat shape will create a bigger force because there's more area, and it's, when the air hits it, it's directly in contact with it. When you have like a sphere, some of the air will, come off the sides and whatnot. So the drag coefficient ultimately will dictate the force. So what I did is I just looked up the drag coefficients. I know that these do change. These are a function of the Reynolds number, which I haven't looked too much into, but it sounds like that has to do with like the viscosity of the fluid and the length of the tube and all kinds of different stuff. So I just went off these, and I did get pretty accurate results as far as that goes. So the function that I used is the force is going to equal 1/2 the density of the fluid times the velocity of the fluid times the drag coefficient times the area that's in contact with the air. So for an example, I went through and did it for all of them because ultimately the area is going to change, and the drag coefficient is going to change for each of these. So for instance, for the circle, I just took the surface area of the circle, 4 pi r squared. This was originally the diameter. Wait, that's the golf ball, sorry. Yeah, so this one's the sphere. So I took the diameter, divided it by 2, that's the radius, squared it, and I divided this all in half because only half of it is, creating drag from the air. So plugged all the numbers in. I did it that was for 7.2 meters a second, gave me 0.0274, which was very close to what we had here. The rest of them are pretty close all the way down. Like I said, really the only thing that changed was the coefficient of friction, or I'm sorry, the coefficient of drag, as well as the surface area. So for the square, for example, we just had, this is for the long side of the square. So like if you're looking at it like this, like the air, is hitting directly on the front of the page instead of like, the side, which would be the short end. So the two long sides, they just happen to be the same length, so I just squared them. So that would be, the surface area in contact with the air times the coefficient times the density of air. This is our elevation, times, or divided by 2. So yeah, that's basically how I did it, and more accurate than I expected as far as the calculations and everything. so I was pretty satisfied there. As far as the discussions and everything, I've been discussing it a little bit with my group. I'm about to go and post everything on mine here and do my discussion with another group, so I'll take care of that right now. But yeah, I just wanted to get this uploaded as soon as possible. I'll include my spreadsheet as well. And yeah, as far as everything goes, pretty straightforward. Really, the only thing that's changing is the velocities and the coefficient of drag and the cross-sectional area for each of them. So, or the surface area in contact with the air. So, yeah, I guess that should do it. Thanks.